All right. So, yeah, the addition of HBr with peroxide, the anti-Markovnikov addition of HBr, I should have looked at this. I know one book we've used in the past says it goes like anti, and it might go mostly anti, but that's just the trans compound is going to be a little more stable than the cis. It'll give you a mixture. The same thing with these carbocation reactions. Any of these reactions that go through a carbocation will do what carbocations do. The carbocation is going to be planar, right? So nucleophiles can come top or bottom. And carbocations can rearrange, right? So that brings us to this one. The major product of this reaction would be this. And the H that gets added would be that. All right, so how does that happen? We protonate the alkene. And we get this cation, right? So we protonate to get the more stable carbocation. Here we have a choice between a primary or a secondary cation. Right, so we make the secondary. And then we get a hydride migration. You remember those, I'm sure. And this gets us our tertiary cation, right? So that's going to be the most stable carbocation in there. Now, I say the alcohol I drew would be the major product. It probably wouldn't be the only product. We probably would see some alcohol, some secondary alcohol. And if we did, it would be racemic, right? This cation is planar, so the water could come from the top or the bottom, either one. Once we get here, water is going to add in. And then water will take that last proton to get us up there. The upshot of that is all these reactions that make carbocations, treat them like the carbocations you dealt with in chapter 7, in chapter 6. Stability, everything you learned about cation stability still applies. Everything you learned about migration still applies. Everything you learned about stereochemistry still applies. There is, happily and unhappily, a way to minimize cation migration in these reactions. So, if we do this another way, if you construct reactions like this, you should always draw your reaction arrow last, not first. All right. So again, this is going to be one that I'm not going to ever ask you to draw this mechanism. Mostly because of the second step. So instead of using H2O plus as the electrophile, the catalyst, sorry.
I can't read what's in the parentheses.
In here?
Yeah.
That's an acetate. OAC. So that is that's what it ends up. All right. So this is a weird sort of reaction, but it's good foreshadowing for something that comes next. All right, so again, electrophilic addition. The pi bond is going to be a Lewis base. Pi bond electrons are going to make a bond to something. In this case, the electrophile is not an H plus, but a mercury plus. This reaction is called oxymercuration in your textbook. And what we get out of that I'm gonna leave the acetates out for right now. There's acetates still associated with that. This mercury, believe it or not, has, so, mercury, we don't have a periodic table. Mercury's a really heavy element. How many of you have played with mercury at some point? Right, you were born in 2002. Sorry, we don't let you guys do that. They were starting to stop that when I was a kid, but if you knew people, and then like 20 years before I was a kid, your drugstore would just have like, it was like a chemistry stockroom, you could get anything. So when I was a kid, you had to know somebody, you had to have a friend whose father or mother, mostly father when I was a kid, was a dentist. Because I don't know why. I just remember that was the case. They had mercury, and so you could play, it's a really fun material to play with. I'll see if I can, trouble is you're over here, like it's hard to, I don't mind so much taking a bottle of mercury from a lab right downstairs to Salem 12 or something. But then, carting it over to green is, if it breaks, I'm fired. So, anyway, you've probably seen it, at least a YouTube video, right? It's a liquid. It's a liquid metal. It's silver. But it is super heavy. It's way down at the bottom of the periodic table. All right. So the reason they make bullets out of lead, the reason they put uranium in armor, is because it's heavy. And so the point is, the actual teaching point is that mercury can expand its octet. It's a huge atom. It's got valence electrons way out, and so the electrons can actually make a bond to that carbocation, and you get this. Right? And so the plot, this is actually 2 plus. So this is 1 plus. There's an OAC attached to it. Never mind. With an acetate, it's 1. It's plus there. The point is that mercury can attach to the secondary carbon and stabilize it. Okay, and so now we don't get. So now there is no migration here. Right? So the mercury stabilizes the secondary carbocation, and it stays stuck right there. All right. And now, like I said, I'm not going to ask you this, but now the water that attacks, we're going to see this type of a cation again when we do halogenation reactions, which I'm going to finish with today. And then I promise I'll stop. Okay, so this 3-membered ring with a heavy atom in it, where the heavy atom's got the positive charge, pretty unstable. It's still, like, the mercury is stabilizing that secondary cation, but it's still quite reactive. And water is going to attack water will attack the more substituted carbon. And this, forever in my life, seemed weird, okay? It looks like an SN2 reaction, but it's attacking the more, the arrows are like an SN2, but it attacks the more substituted carbon because that carbon is the more partial positive. It's the more electrophilic carbon. And then this gives, ultimately, so you got to lose a proton off there. This will ultimately give this organic mercury compound with the OH on the carbon. So it's Markovnikov addition. The ultimate product's going to look like Markovnikov addition. I've really screwed up my board here. So this is the product of step 1. Let me change colors for step 2. The sodium borohydride, again, you're going to see sodium borohydride and have to know more what it does in Orgo 2. But it's a reducing agent. You've got H's that react like H minus. And basically what happens here, you have a hydrogen add to the mercury and to the carbon. And so you wind up kicking the mercury out of the molecule and getting addition of the H. All right? So oxymercuration is a good way, you really synthetically, if you want to add water across a double bond, and you want Markovnikov addition, but your cation is going to be really unstable, you want to do an oxymercuration. Now, everybody kind of chuckled when I said, have you ever played with mercury? Because you guys are like chemically literate and know that mercury is, you may not know all the ins and outs, mercury is a hazardous compound. Right? Mercury ions aren't really that bad. But it's easy to oxidize mercury ions to mercury 0, and mercury 0 is bad. Organic mercury compounds like this are really nasty. Okay, so these are not terribly safe reactions to do. And then in terms of expense, like if you're a chemical company, paying to safely get rid of waste is a big expense for chemical companies. So they're always looking for people to come in and figure out how to make things more efficient, minimize waste. Paying for waste that's got mercury in it is, I mean, basically you could not convince a company to use this process anymore. And so we actually do, we've sort of replaced mercury in this reaction. Anybody want to hazard a guess what element we use in place of mercury? It's a symbol of how expensive it is to deal with mercury. We use gold. So gold is, you can drink gold. People did. Makes you live forever, right? Everybody knows that. Okay, so we can use gold. For those of you who want to take Chem 223 in the spring, your professor there is going to be Dr. Amanda Jones. Can't emphasize this enough. There's no relation between us. I'm sure there is, like back in Wales in the 1300s. I'm sure there's a common ancestor somewhere. But anyway, she does research on gold catalysis. So you know how you distract Dr. King with sheep? Ask Dr. Jones something about gold catalysis. And you'll have to take notes because then she'll probably put it on an exam or something. All right. Last thing for the day. Oh yeah, I meant to mention there, aside from joking around, that I've gotten a bunch of response, but I did send you guys an email in response to Dr. King sending me an email asking me if I had generated a list yet. I guess I was supposed to do that or something. So anyone who wants to be enrolled in 223 and the lab needs to contact me by the end of the week. And then I'm going to take that list, I'm going to give it to the chemistry department, and they will just like put you in there. And the reason for that is if we don't get you in there, you're all freshmen, right? So if we don't get you in there, then upperclassmen will just swoop in and take all the spots. And we don't want that. Yeah.
If you put us in there, will that like not count on the round 1 registration?
I think it doesn't count on the round 1. I don't hold me to that one.
That's really
No, and I also think it changes like year to year. So I'm not sure how it works.
Because that's how it worked for this.
Yeah. No, it's just the other thing, and maybe you guys aren't aware of this. Once you've declared a major, your department will just enroll. Like I'm doing major advising chemistry right now, and it's basically okay. You want to take? We're going to put our chemistry majors in the upper level chem classes before anybody else can come and take them. But you know, all the people that want to take P-Chem on campus who aren't chemistry majors. That there's like, I mean,
Really
hundreds of them, right? Yeah. Yeah. Anyway, last reaction for the day. We'll pick up with this next time. All right. So, if you treat an alkene with Br2 or Cl2, not I2 importantly, Br2 or Cl2, oh crap, sorry. You get anti-addition of 2 Brs. So if it's a ring, it's going to give you a trans product. This is always anti-addition. Right, so the mechanism here is a little weird. You would not think of Br2 as being a Lewis acid, but it is. Bromine's very polarizable, remember. bromine and iodine, chlorine less extent. This reaction really does go a lot better with Br2. Br2 is a liquid. It's toxic, but it's liquids and solids are always easier to deal with, handle than gases. Because gases, you know, you can not see them and you can breathe them. Breathing them is a great way to get them into your system. Liquids and solids, you basically have to eat or drink. Okay, so don't eat or drink chemicals in the lab. But you know, chlorine gas is super toxic and it's a gas. So you don't know you're breathing it until you're in trouble. Okay, so Br2 here, the mechanism then, it's polarizable, you get this instantaneous dipole, the pi electrons attack, break the bromine-bromine bond, and then this gives, right, the cation you would expect from this would be that, right? Based on what we did with HBr. But just like with mercury, this bromine now is large, it can expand its octet, and it's got these electrons right around it. And so the bromine can actually just clamp down here, and you wind up with a bromonium ion. Bromonium. All right, and here's the thing. I've drawn this intermediate here with a cation that the bromine then attacks. Right? I've kind of made it look like we go straight from the alkene to this carbocation, and then the bromine does this. Really, this just goes straight to the bromonium ion. Right? It's more or less a concerted addition. The one Br adds to both carbons, and then the Br minus gets kicked out. And then, like I said, you've got Br minus here. So let's say this bromide is above the plane, right? So if the bromine's above the board here, the bromide has to come from the back. And this would give us, right, this bromine is going to stay above, and the one that comes in has to attack from behind it. This used to be a chemical test, so in the days before spectroscopy, you would figure out what was in your molecule just by doing, you'd do all these different reactions with it and see how it behaved. And so if you thought you might have an alkene in there, you would mix your compound with bromine, and if the bromine color went away, you had an alkene. Right? And again, this is one, if I was in Salem right now, I used to do this one in class. It's really fast. Maybe I'll bring it around to the lab next week. I said that was the last one. The other thing I'm going to say is, if you have this in water or in alcohol, this is what I'll start with next week. Right? Water is a better nucleophile than bromide. Water is a stronger base than Br minus. And so this is not the full mechanism. Right, this is called the halohydrin reaction. So when you go to look at this, all that's happening, anytime there's Br2, so this would be if you did Br2 in water, say, the Br2 is going to react to give the bromonium, and then if there's water or an alcohol around, like if that's the solvent, that's going to be the nucleophile that attacks. If there's not, if you don't have any water, you'll get Br2 adding. If there is water or alcohol, you'll get a Br and an OH. And in the halohydrin, this works fine with Cl, Br, or I. So that's a large amount of chemistry for a day. Yeah.
What's the double arrows?
So this, if I put up a double arrow like that, what I mean is there's a couple of steps here. So like water attacks that carbon, you get the bromide. The first thing you're going to get is going to be a protonated, this alcohol is going to be protonated. Okay, so I think I'm going to maybe have some office hours tomorrow. I don't know yet. I've got a bunch of advising meetings. I'll get that up. There'll definitely be a lot of office hours next week. You will get your exam on Tuesday. You guys have lab on Monday, right? You might get your exam on Monday in lab. We'll see how the weekend goes. Go out and enjoy the beautiful day. I will see you later. Yeah. Yeah, that was actually the thing I never said that, did I? I sent you guys an email about Chem 223. Please reply to that email if you're interested in taking it. All right? If you just tell me you want to take it, I'm going to assume you also want the lab. Or you can actually do the lecture and the lab separate. But you have to do the lecture before the lab. So you could just take the lecture if you wanted. Pre-med and chemistry majors require the lab. So probably you want the lab. All right, see ya.
I'll respond to that tonight. I might find you maybe today. So I'll just
Okay.
do that and then.
Yeah. That's good.
I emailed you about the.
I saw it. I haven't processed it.
Okay.
What I would say is I've already said no to 2 other people with that
Yeah.
issue. I get it.
Yeah. Okay.
There's-
The main thing was also like the rules for New York. Like